Hello children! This video covers linear and angular velocity. In your textbook, it is chapter 6, section 2. So before we get into like notes and things, I want you to just imagine for me that there's a carousel. Right? It looks beautiful and lovely and sparkly with all kinds of cool creatures on it that you can sit on and ride around, around. And I want you to pretend that, let's see, Mr. Ware is riding a horse on the very outside circle, and that I am riding a unicorn on the inside circle. Okay, so basically we're starting at the same standard position, if you will, like that vocabulary that we use with the linear circle, or sorry, with the unit circle. We're both going to kind of start in a standard position, and the carousel is going to rotate counterclockwise. Let's say about, I don't know, 50-ish degrees, maybe 60, whatever this may be. And it's going to bring us, instead of our starting point here, we're going to rotate some sort of distance till we get to two different stopping points. Mr. Ware will stop here. I will stop here. So basically what just happened was that we had an angular displacement, right? We had a starting position, and then if you traced over along the curve, along the carousel, there was an angle created here that we both just traveled. So let's write that down first. This is called angular displacement. Let's make this a little bit bigger. Oh, and spell it better. Displacement. Okay. Angular displacement, in simple terms, is just the angle created by the movement of an object along the curve of a circle from one point to another. And usually this is, especially in this chapter, we are going to refer to that angle as theta in radians. Theta in radians. So we both were displaced by the same angle. Now, our angular velocity is different than our angular displacement. So angular velocity, when you hear the word velocity, if you think to your physics experience, velocity may hopefully trigger the word speed in your head. So it's not just a distance, and it's not just the time, it compares the distance to the time. So when I talk about angular velocity, I am talking about how much of that angular displacement are we covering in a certain period of time. So let's define that now. Angular displacement. No, I'm sorry. Angular velocity. So angular velocity. I wonder if y'all can hear my dogs fighting in the background. If so, welcome to, a day in the life, I guess. The angular velocity is going to be considered the ratio of the change in the central angle to the time. Now, again, velocity, probably the one we're most familiar with is our speed of travel in a car, right? Miles per hour. So that ratio just compares those two units, except instead of miles per hour, the distance that we're talking about is that central angle. Okay, that central angle and the time. So this central angle that we're talking about, again, needs to be theta in radians. And then time could be minutes or seconds. It just kind of depends on the problem. Oh, now they're drinking water very loudly next to my microphone. Maybe you're laughing. That'd be nice. Okay, so now there's a formula for angular velocity. So we've got, we use the lowercase Greek letter W. It's actually omega. So that stands for angular velocity, which I'm okay with you as abbreviating as AV. Angular velocity is equal to the ratio of the change in the central angle. So that change in that central angle will be theta over t, where theta is going to be the angular displacement in radians. Okay, so you need angular displacement before you can find the angular velocity. So my question is this: if we are on this carousel, do Mr. Ware and I have the same angular velocity? Are we traveling the same angle, the same angular distance in the same amount of time? And hopefully you answered yes, right? The carousel spins just constant. It does not spin unless you're on a crazy carousel where it has different levels, or, it has different portions where maybe the inside circle spins at one velocity or at one speed and the outside circle is spin at another speed. But, the constant spinning of the carousel means that we would both cover this same, perhaps, 60 degrees in the same amount of time. And again, we're talking about in radians, so maybe I should have put a radian there. So we have the same angular velocity. So let's just do a random example of how to calculate angular velocity. Let's see. If I ask you to find, well, let's do an angular displacement example first. Find angular displacement. And I'm okay with you abbreviating that as AD. Find angular displacement in radians of 3.5 revolutions. And I want you to round. Oh, this doesn't do shortcuts apparently. Oh yeah, it does. Round to nearest tenth. Now, as you're writing this in your notes, feel free to not write out every single word. Abbreviate what you can, and you don't have to put the directions necessarily. But I'm letting you know to round to the nearest tenth. So find the angular displacement in radians of 3.5 revolutions. Well, let's go back to the definition of what we said angular displacement was. It just says the angle created by the movement of an object along the curve of a circle from one point to another. So things to remember. No matter how small or how big a circle is, it always has 360 degrees. In radians, every circle ever in the world always has 2 pi radians, no matter how small or how big it is. So Mr. Ware and I, even though we are on different size circles, if we made one trip around the carousel, we would both have traveled 2 pi radians. So no matter the question, or no matter the size of the circle, in an angular displacement problem, if I'm talking about 3.5 revolutions, it does not matter what size circle is revolving. Why won't it let me write? There it is. Oh, I wonder if my pen died. Wouldn't that be nice in the middle of this video? Maybe I have to write my finger. Uh-oh. Nope. Technical difficulties. I'm having many of those this morning, apparently. There it is. Okay. 3.5. There it is. Okay, 3.5 revolutions is, no matter the circle, you will always travel 2 pi. So this is actually a really simple problem. All we're doing is taking our 3.5 revolutions and we're traveling to a distance of 2 pi radians all the way around. So the angular displacement is going to be, we can simplify this like just one step if you want to put 7 pi radians. But since it asked us to round to the nearest tenth, when you type in 7 pi in your calculator, it's approximately 22. Let's see if there's a decimal. It rounds up to approximately 22 radians. So a couple things to note. First off is, in my last video, I tried to stress how radians typically were answered in terms of pi, but that's not always the case, as given here in this example as well. Something else to consider, because I haven't mentioned it yet, I've kind of been assuming that you're doing it, is anytime you enter pi in the calculator, make sure you use the pi button right under the clear button on the caret, and don't ever type in 3.14. The pi button is going to be a lot more accurate. Okay, so that's the angular displacement is 22 radians, so that's after 3.5 revolutions. So let's take this type of example and take it one step further. Next, I want you, if I can spell example correctly, next I want you to find the angular velocity. Again, you can call that AV if you want. Find angular velocity. If 8.2 revolutions are completed in 3 seconds. If 8.2 revolutions are completed in 3 seconds. So now I want you to actually tell me the angular velocity. So we need to use the formula that we just learned up top. Angular velocity, we use omega. The formula for that is omega equals, we said it's the ratio of theta to t, where theta is the angular displacement. Angular displacement. And then t is equal to time. So notice my problem gives me nothing about angular displacement. It gives me time, it gives me 3 seconds, which I know that is t, but 8.2 revolutions is not the displacement. That's just how many times I go around. So before you can solve this, or before you can plug things in the formula, you need to go ahead and find the angular displacement first using the revolutions. Well, just like we did in this problem, you're going to simply multiply your 8.2 revolutions times 2 pi to figure out what is that angular displacement. And again, you could do 16.4 pi, or you can go ahead and actually type that in your calculator and get a decimal. But what I recommend is, so that's about 51.5. So that's angular displacement. So going forward, what I recommend is when we now have omega equals, for theta, if you're going to use 51.5, make sure you leave that long decimal in your calculator. And then divide by times 3 so that you aren't rounding twice, so to speak. Or you can just put 16.4 pi divided by 3. Now, let's put units here. This is going to be 51.5. When we talk about angular displacements, these are in radians. We can put rad radians. Per time is in seconds. So omega, our angular velocity, anytime we have a velocity, it's going to have, it's the ratio of distance to time. So then omega is going to be approximately, I think 17.2, and in terms of units, they're already here. It's going to be 17.2 radians per second. You have to make sure all of your answers have the correct units. Okay, so angular velocity will always have an answer of the angle, right? Angular velocity, an angle per time. So maybe you want to make a note of that somewhere. Oh, what just happened? There we go. Okay, angular velocity will always have an answer. Answer in radians or radins. Wow, good spelling. Radians. Of course, it's not right now. I don't know. All right, you get what I'm trying to write though. Radians per time, whether that time be minutes or seconds. Okay, so that is angular velocity. The last thing to discuss is linear velocity. So hopefully the word linear makes you think of the word line, which, we all know what a line is. So let's go back up to the top here to our little carousel. And I want to talk about the difference between my linear velocity and Mr. Ware's linear velocity. So my question to you is this. If we are riding the carousel and we're traveling, the carousel is rotating at whatever speed it wants, we are traveling the same angular distance, right? In one revolution, we will have both traveled 2 pi radians, but our linear velocity might be different. Particularly, which one of us do you think would feel like we are going faster? So I'm closer to the middle. Mr. Ware's hanging on to the very, very edge of the carousel. Which one do you think would feel like is going faster? So if you haven't figured out the answer yet, it's awkward asking questions on a video. If you haven't figured out the answer yet, consider the fact that if I start here, it's no longer writing. That's fantastic. Oh yeah, it is. There we go. Okay, if I start here and I have to travel here, that's a relatively short distance, right? Linear distance if I unraveled that. Mr. Ware, on the other hand, will start here, and he will have to travel all the way. I'm now writing with the mouse instead of the pen, so it looks lovely. And he's traveling all the way to this spot. So in the same amount of time and in the same amount of angular displacement, Mr. Ware had to travel a further distance in the same amount of time. Therefore, he should feel like he is traveling faster, even though he's not.